Here we are, back with the 2015 mechanics paper. This is question 2, which is called forces. And having a look at this giant, great big fat old wood pigeon, the kereru. I think this is what this question's about. The kereru, also known as the New Zealand wood pigeon or kukupa, is one of the largest pigeons in the world. First thing, explain the difference between mass and weight. Very common question. So mass, which is measured in kgs, is the amount of matter in an object. Whereas weight, measured in newtons, is the force of gravity acting on an object. So I'm just not quite sure if we want anything else here, so let's have a little look. Oh, I think that's quite good. Okay, where it says explain the difference, we probably want to put mass is the amount of matter in an object, whereas weight is the force of gravity acting on an object. We could probably add a little bit more in there, like the amount of matter does not change. So our kgs is always the same. However, our weight will change if we are in a place with different gravity. Really, for us, that would have to be a different planet. And that's not likely, of course, but possible. Calculate the weight of a kereru that has a mass of 630. Little bit of a trick question here because that's in grams. So I need to change that to kilograms. So I need to divide that by 1,000. So that is going to equal 0.63 kilograms. 630 grams divided by 1,000. And our weight force has to be the mass in kilograms times gravity. That's a bit of a mean question actually. Equals 0.630 times 10, which equals 6.30 newtons. So that was a bit nasty. You don't often get grams given to you. So yeah, let's hope that doesn't happen this year. Over the page, we've got a picture of our kereru flying at a constant speed, but then slowing down. Only horizontal forces. That tells us that we don't need to worry about gravity or support forces or lift or anything like that. So it says, assume any other forces are balanced. Okay. Referring to the force diagrams above, explain the link between the horizontal net force acting on the bird and the type of motion. As soon as we see something about forces and motion, we should be really prepared for this question. So, what is meant by the net force? What is the link between the horizontal net force and the motion for each situation? So I'm going to have to make 2 answers, one for constant speed, one for slowing down. Compare the direction of the horizontal net force and the direction of the motion for the bird. Okay, lots of help there, but really we should be quite good at this by now. So let's define the net force first. So the net force is the sum of all forces acting on an object. And just a little side note, we probably don't need this, but if I've got 2 forces acting in the same direction, they add together. And if I've got 2 forces acting in different directions, we subtract those from each other. Okay, so let's talk about the constant speed. So let's name the forces first. So there is a force pair. Here is my force pair here. So there is a force pair of thrust in the forward direction. You could probably just label that on the diagram. And friction, which is the opposite force. You could put drag for that if you wanted, or air resistance as well. So if we look at a constant speed and shown by the size of the arrows, we can see that these 2 pairs are balanced. the forces are balanced. And if we've got balanced forces, that means we've got a zero net force. So therefore, there is no net force. A little bit tricky in this one, because if we've got zero net force, there's one of two things happening. Either the object is stationary or stopped, or it's going at a constant speed. Because this bird was already flying, it is going to continue to fly at a constant speed due to the net force being zero. There is no net force, therefore the keriru continues to fly at a constant speed. Okay, so now we've got the other diagram, which is the slowing down, and you can see here that the friction force is still there. The thrust force has actually been taken away. So these are obviously not balanced anymore. So we're going to say the same force pair is now unbalanced as friction is greater than thrust. This means there is a net force, and we have to say which direction this net force is acting in. And when we want the direction, we want to say, is it acting in the same direction or the opposite direction to motion? And here, obviously, the net force, or the bigger side, is away, the opposite direction to the direction of the bird's movement. So we're going to say down here, this means there is a net force acting in the opposite direction to the bird's movement. Okay, if our net force is acting in the opposite direction to the direction the object is moving, that is going to cause the object to slow down or decelerate. This causes the bird to decelerate. So you're going to get a question in your exam that asks you this kind of thing. The only thing there's two things I haven't covered here. One is if the object is speeding up, and in that case, the net force will be in the same direction to the object's motion. And the other thing I haven't written about here is if the object is stationary, and it has to be stationary to start with, and then the forces remain constant. So you have to be really good at recognizing that it doesn't matter if it's a bird or a person or a car or a boat. If you have to talk about force pairs and balanced or unbalanced forces and net forces, this is the kind of linking you need. Be really clear with your linking, and may I suggest that you do the linking in the order that I did it. Okay, over the page, now we've got this beautiful graph, and it's a speed time graph. First thing to do is check, is it a speed time or distance time? So it says, use the graph to explain which bird has the greater acceleration in the first 3 seconds. Calculation is not required but may be used. I would always use them if I could. What I need to recognize is that on a speed time graph, the slope equals acceleration. If I had a distance time graph, the slope would equal speed. So that's something that we need to know. So I can calculate the acceleration of bird A. I'm going to label bird A so they know who I'm calculating it for. Acceleration equals change in speed over change in time. Bird A is this line here. So N is the first 3 seconds. There's 3 seconds. So bird A, which is the blue line. So if we look here, that's quite a tricky one. I'm going to go 7.5 meters per second. It's changed in 3 seconds. 7.5 meters per second over 3 seconds. That's 2.5 meters per second. And bird B, come up to the graph, 3 seconds. That's this one here. I'm going to go, that's 9 divided by 3. Oops, sorry. And that's going to be 3 meters per second. So then I can make a statement, bird B has the greater acceleration. So I do need to answer the question. The other way I could have answered this question is to use the gradient without calculating. And I would say that bird B has the steeper gradient. So therefore a steeper gradient means a greater acceleration. So that would be the other way to answer that question. Right, in 16 seconds, bird B travelled 121.5 metres. How much further did bird A travel in the same time? So I need to calculate the total distance of bird A in 16 seconds. Coming over to my graph, that's the entire graph, 16 seconds. So what I need to know here is that I need to calculate the distance equals the area under the graph. Now the best way to do this is to divide it up into triangles and squares. If you know how to calculate the area of a trapezium, you may do so. I prefer to do the triangles and square. So bird A, I'm going to come down here like this. So I've got this triangle here, and then I'm going to come down here like this. And I've got this triangle, so I've got triangle, so I'm just going to call that A, B, and C. So I'm going to label those sections. So section A, and I've got a triangle, so that is going to be half base times height. So let's look over here. Base is going to be 4, and the height is going to be 10. So it is half of 4 times 10, which equals half of 40, which equals 20 metres. Right, section B. Now if we look over here, section B is a square, so I'm just going to go base times height. So if we're looking here, my base, now I don't go from 0 because my square only goes this bit here. So the base of my square goes from 4 to 14, so that's 10. So it's going to be 10 times, I've got to go all the way up, 10 times 10. So that equals 100, sorry, not showing it, 100 metres. And finally section C, which is another triangle, so that's going to be half base times height. If we look here, the height is the same, it's going to be 10, but this time our base is only 2. So it's going to be half 10 times 2, which is half of 20, which equals 10. So now I'm just going to add those together, 20 plus 100 plus 10, so the total distance equals 130 metres. What did the question say? How much further did bird A travel? So 130 minus 121.5 equals 8.5 metres further. So always make sure you go back and make sure that you've answered the question. And that's the end of question 2. Boom, done.